Okay, so let's start. So this video is being recorded in order to document the utilization of Open PLC. So before we start, let's go into Open PLC. So when I type in on browser Open PLC, I end up with this resource. So it brings me here to this particular resource when we see the new name for Open PLC, which is Autonomy. So they now have, I think, some industrial clients today. They rebranded, but they're still free. So in my case, when I do the videos and the educational items for ladder diagram programming, I now always use OpenPLC as a default platform. So the reason why is because it's not vendor associated. Well, they have a line of Raspberry Pi and Arduino PLCs that they typically use. And these are really good PLCs. If you look at the general picture, they're affordable good PLCs. But the problem is they cost, well, not so much for these ones, but for the industrial ones, they cost an arm and a leg. So it's very expensive to learn ladder diagram programming using a real PLC or industrial grade PLC. You're much safer using a Arduino Nano. Okay. If you're just trying to learn about programming. So, okay. So this is an Arduino Nano. It costs 26.8 euros. Hell of a lot of money. Okay, if in the Philippine standard. But again, you can buy it cheaply here in the Philippines because we're close to the manufacturing base, which is China and Taiwan. Okay. Even the Philippines does manufacture some chips. Okay. SGS Thompson does. And ST Micro does. Okay. So when we go back to this one with ano nga to? Um, headers and terminal blocks. This is now the perfect means for me to do programming or to introduce programming to students. Okay, when I use this one, which is the one in front of me now. So I have inserted in it a Taiwanese manufactured Arduino Nano uh, and a similar okay, terminal breakout board wherein you can just basically wire in or screw in wires that go to specific locations. Now, the suggestion is for students to have something equivalent to this one. So in the laboratory, we're using the Alexan Digital Trainer. Well, the first ones that Benjo Tirol and uh, Dr. Alexi developed. Okay. So ito. These are the ones that we've been using. Okay. So they're kind of a perfect fit because you just place in the Arduino here with the board and then you stick the specific elements into the slots, okay, for the digital planer. And this basically has a 220-volt supply built into it. Okay, servicing is a lot more easier. So you have to I have to always hand it to my former boss and his employee that they did a very good product or they created a very good product. Okay. So my hats off to them. Okay. So of course you can choose another type of digital trainer. The only requirement is that you have switches. You have output devices which are basically LEDs so that you can track what actually is happening to to the device itself. Okay. So next, when you're using a Nano for an output, you now have to abide by the rules. So Open PLC lists a default set of five input pins and four output pins. So these are uh, 2, 3, 4, 5, 6. We all know, for those who program using Arduino, that normal Arduino, not the every, but the older nanos, they actually have pins 2 and 3 as the interrupt pins. So if you want something to be serviced by an interrupt, use these memory locations or these Modbus addresses 0.0 and 0.1. I, X. Okay. So IX is a designation for an input. The designation for an output is a QX designation natin. So the way that you read this in terms of computing sciences is that the first number represents the byte location or the address location. The dot and following number represents the bit location natin. So in this case, you're looking at bit 1, bit 2, bit 3, bit 4, bit 5. Okay? So, et cetera. Dun sa ano natin. So, ganun rin dito. You're looking at word address 0, and then followed by bit 0, bit 1, bit 2, bit 3. Okay. So, let's take a look at Nano. Arduino Nano. Just to put some context, admin, pin assignments. Why they selected that sort of thing. Okay. So, datasheet. Okay, we have Chinese na nakalagay dun sa loob. This is a better one. Okay. So let's expand this one and we can see further why the selection is done that way. You can see here PD values here listed. This belong to a specific register. So they're all belonging to the same register. All values of D listed here. So we're not using D0 and D1 because this is exclusively used for communicating to the device. Remember, in PLCs, we communicate using Modbus. Okay. So this is for Modbus. So it makes more sense now why the inputs are just limited towards 6, D6 in this case. We're not using D7 because traditionally 7 or the last bit of the element is actually used to indicate a sign. Okay? O yung whether it's a negative sign or positive sign here. Okay? Now, the odd part is this one. Okay? We started off with 8 and then we proceeded to 11, 12, and 13. So we're basically just using PB0, PB3, PB4, and PB5 for this particular output consideration. But again, since they're all Bs, this is basically word around the register B. And this is around the register D. Okay. So that puts the, or places the I/O configuration in terms of something we can better understand from the computing science aspect. Okay. When we're looking at analog input data, we're using a word to store the information. Okay. So the word in this case is what or how long. Okay. Let's go to documentation. Hopefully it works. Previously, some time ago, I tried it, didn't work. But from what I can remember, this is a 32-bit word. So meaning to say, your number can go up to 2 raised to the 31. Okay? Kasi again, you have the negative aspect to it. Okay? So it doesn't work that way dun sa kabilang side. So these are 32-bit words. So again, let's do a calculation. 2 raised to the 31st is 2 million. No, sorry. 2.1 billion yung size na kaya niyang store. So this is basically the length of the registers that we have here. Now, if we're looking at 8-bit words rather than 32-bit words or 16-bit words, we can look at, again, calc. Pinatay ko agad. 2 raised to the 15, 32,000. Not too much unreasonable number. Okay pa rin yan for our purpose. Okay. So take note, I'm not using 16 because there's a side bit, yung last digit natin. Okay. So let's go back. Okay. So when we're doing assignments here, okay, let's open a project. So I created a project earlier called PLC Stepper. Select folder, program 0. Meron na ito naman. Okay. So this is for a different stepper motor. Close project. Okay. New. I'll create a new folder. So I'll call the folder PLC test step M4183. Okay. And then I'll select this folder. Okay. So write down the name, stepper M413B. Select the language. So in this case, we're using ladder. This is free body diagram or functional block diagrams, and this is script. So we use only LD. Okay. So let's go back to this one. Okay. So to add a variable, you now need to consider what you want to use. So you need to understand and you need to remember what IOs there are. Okay. So in this case, I'll say D13, D13, and type Boolean. So Boolean is used for input pins and output pins. The location again is 0, Q, X because it's a Boolean value. 0, which is the output 0, and the bit number 3 natin. So again, this is pin 13, which I am designating as the clock. Okay. So when I place in plus here, it does a magic thing. Nag-a-add na lang siya. Okay, but I don't need an addition. I need a subtraction. Okay. So yan siya because this one is now designated 12 for direction. Okay. So, ganyan yung system. Okay. When I place another one, I make this into number 11 ba? Sorry. This is the reason why it's turned on. So I can always go back. 87. The 8. So I change this to 1. And I change this to pin number 8, which I imply for use with enable. Okay. So let's do a program. Okay, so in this case, I need a left power rail with uh, 4 connections. I need a right power rail with 4 connections as well. Tapos, I need to add in, I don't need any inputs here because this is a freewheeling experiment. So no outputs or input pins necessary to control the function. Okay. So let's place in the variables first. Okay. So this is for 8, which is enable. It's normal. Let's write in for pin 12. Normal din siya. So notice I did a sequence wherein I did these first two items first. Yung enable, which is 8, and, and direction. Okay. My clock, on the other hand, I'm not yet putting it into play because I need a counter to do the action. Okay. So a counter can be taken from the functional block. Okay. So we have a standard functional block here. Okay. Always use this one if you want to migrate your ladder diagram program into the industrial PLCs. Okay. So we have the reset flip-flops, a semaphore, which is basically a container for digital memory. Okay. Uh, we also have the count up, which we have the count up signal, a reset signal, and a preset value, which is the count at which Q changes. Okay. Q becomes equal to high. Tapos we have the current value for the count. Okay. So we have the countdown timer, we have the count up timer, okay, both up and down, reset and load the values. Okay. So, and then we have this one, which is the test pulse or timer pulse. Okay. So in this case, it says here it's supposed to give out pulses. Again, sometimes the wording that they use here is not that good. Kasi hindi siya, it's not reflective of what really does happen. Okay. But we'll use this one. Okay. So, in this case, I'll place in an in value here. I'll raise this up a few times, and then we'll lock in the value for our clock, which is the 13th pin. So, as you can see, I renamed the pins, so it would be a lot more easier to look at. Okay. So, next, we need a variable. The variable that we can place into consideration is now based on time. So, if it's time, we always place in T vox or T hash. And then we place in the value. So, for this one, we'll use a smaller volume na 20 milliseconds. Okay. So, this 20 milliseconds is attached towards our PT value here. Okay. So here, you can see there's a shades here. The shades is actually a icon for lookup. So the lookup value for clock, the lookup value for deer, the lookup value for enum, and the lookup value for Q natin. So in this case, if I double click the clock, I should be able to, yun, okay. So you saw an error. Okay. I think this is the only issue I have with Open PLC. But again, because it's free, it allows you to do something with lesser amount of resources. It's something forgivable na. Okay. So let's try to run the simulation. Okay. Change the range to 10 milliseconds and then stop and do a program run once. Okay. Nakita nyo, false pa siya sa unahan. As time passes by, well, stop natin. Tapos run ulit natin. So, did you notice anything? It doesn't move at all. Okay, yun yung problem niya. Okay. So, if this is the concern or this is the issue at hand, that it doesn't quite move, we have issue with regards to the signal pulse. Okay. I'll show you kung bakit. Let's move it to a smaller value. 2. Let's run the program. So 2, tapos nag-fall siya and then stays false all the way. So it doesn't anymore change. Okay. So yun yung pinaka problema dyan. Okay. So let's save this one. So for this one, we therefore need something else entirely different. Okay. So let's turn this back to 20 ms. And let's do a repeat, rinse and repeat. Okay. So I'm now going to take out the clock from this rung. I'm going to move it to the bottom rung. Dito sa kabila, sa TP1 natin. Okay. And now I have to insert something. Kasi seemingly the problem is the TP0 is not being reset. So it doesn't generate clock pulses. It actually generates a changing rising value or falling value of a clock pulse. Okay. So in order to trigger this one, pabalik dun sa kailangan natin, we need to do some revisions. Okay. So I placed in here clock. I am now placing in another variable. Okay. So this variable I'm including here is no longer a clock. This is just a reset point. So I'm removing this one kasi it's not a valid output to reset TP0. Okay. So lalagay ko lang siya dito. Again, this is the biggest difference of why a ladder diagram is different from a lot of different things when it comes to programming. Because you can actually see here that the output can actually also become an input. This is not something that you see normally in a program, but it can be done that way. So, ganyan siya. So, reset PT. Okay. Tapos, we can include here some values ng clock natin. Okay. Maybe it's premature to move the clock. Balik ko lang ulit siya. And on the other side, we place in the clock as a normal value. For an input trigger pulse. Okay. Maybe I should put it to negated. Tapos, I can place here my reset pin as normal and sequence it towards the last portion. Diba? Okay. So let's run it. You, as you can see, the clock is now handling it correctly. Okay, stop. So we're getting that the clock pulse occurring in the output natin. Okay. So next, let's do a save. Okay. And let's generate the program. So I have here a Arduino Nano. This is an R3 model. It's connected to COM22. I'm transferring the program to it. Okay, so it generates the binary file, which is basically the hex file. That's a compile process. If you have a antivirus software, the antivirus software will try to intervene here. So now I'm able to see the action for my output, okay, on my Arduino Nano. Okay. So ganyan lang siya. Okay. So if I want a smaller value here, let's say 2 seconds on and 2 seconds off to reflect on my Nano, I can just change the values here and then uh, redo the software code. Okay, keep running. Serial discovery kasi yung ginagamit niya in order to push that one out. So that's it. So this is how you utilize a Open PLC and load data into another device. Okay, so in this case, I'm using a Arduino Nano. Okay, so the metrics do change if you're using an ESP32. Okay, so that's about it. We're done with this one. I'll stop recording now.